So let's look at an example. This transfer function is more complicated than what we just did for the basic ones or the straight line approximations. And let's see if we can figure this out. So in this case, tj omega is going to be equal to, so in this case, I would like to know the straight line approximation just for the gain function, plot. So tj omega is going to be equal to 10 j omega over 1 plus s over 10 and j omega over 10 and plus 1 plus j omega over 1000. Right? So let's see if we can break this in 3 terms. So in this case, this is going to be equal, the first term is j omega over 0.1, and the other 3 terms are the same. The other 2 terms are the same. So I'm not going to write that. So therefore, the gain plot tj omega is just equal to, let's see, we have 20 log base 10 j omega and minus 20 log base 10 1 plus j omega over 10, right? And minus 20 log base 10 1 plus j omega over 1000. So in this case, the first one here is going to be j omega over 0.1, right? I think I forgot this. Yeah, there's 0.1 there. So let me rewrite here, j omega over 0.1. So in this case, the first term represents a straight line, right? So let's draw there are 3 lines here. So the first one here is, the first term here is the straight line that 20 dB per decade. So this is a straight line for 20 dB per decade. Let's see, in this case, this cross 0 at 0.1 hertz, 0.1 radian per second, right? So let's maybe draw this 0.1, this 1, this is 10. So another one here is, we have the second one here is negative 20 dB per decade. So maybe I should change the color for these. For the second one we have, let's just random change a red color. So in this case, I have a second term. So that rolls off at negative 20, right? And then I should go on to, so this one is for the second one, which is the negative 20 log 10 1 plus j omega over 10. Okay, so this is this one, and so all this slope has either positive or negative 20 dB. Okay, so right now, if I don't label that, so in this case, let me change the extend this axis a little bit longer. So in this case, this is the omega. So now I have 100, I have 1,000, I have 10,000 here. Maybe I should use the exponential function. So 10 to the power 4th. So in this case, the last term is just very similar to the second term. Now the only corner frequency is at the 1,000 radian per second, right? So let me redraw the third term. So the third term is going here and then drops to negative 20 dB per decade, right? So in this case, the first, let's start with, so now I need to add these 3 lines together, right? So in this case, below 10 radian per second, because since the second term and the third term are zeros, both are zeros, so I only need to draw the first term. Let me change the nice magenta color. So in this case, I'm going to just follow the first line here until to the 10 radian per second. Now, because this has a positive 20 dB and that has negative 20 dB, now this curve will become flat here and go until to 1000 radian per second, right? And then in this case, at 1000 radian per second, this start, because the third term may have negative 20 dB, and this becomes negative 20 dB per decade. I'm not drawing to the scale. So in this case, so there should be let's see what the T max here. Oopsies, I'm going to try the color. So let me draw the color here. So what's the T max here? The T max, this should be 40 dB, right? Because this is 2 decades. So 1 decade, another decade. So therefore this is 40 dB. So this is 20 dB. And so the T max is 20 dB. It is 40 dB, right? So this is the T max. Remember what the T max is, the maximum gain function. And in this case here, when you drop from the 10 from 1000 radian per second, so you drop by 10 40 dB, then you should drop in 2 decades. So this should be 10 to the power 5th, right? So the line should pass through right at 10 to the power 5th radian per second, and or 100K. And so this is the straight line approximation. In this case, we have a band pass filter, right? The shape. So the pass band is between 10 radian per second and 1000 radian per second, right? So this is the, and also have the Python draw exactly the curve. And if you look at that curve, look at that, right? So pretty close. So in that case, we have so passing at a 0.1 radian per second, we're passing through the 0 dB line, and then we go 20 dB per decade until to 10 hertz, 10 radian per second. I keep saying hertz, not hertz. So, and then goes all the way, go flat, turn flat, because the second term has negative 20 dB, because that's a pole, right? You hit a pole, so you reduce the slope by 20 dB per decade. And then you go flat, hit the third term that has a pole, another pole there, and it's 1000 radian per second, and you become the slope of negative 20 dB per decade, right? So that's the, and you can see that across this 0 dB line exactly at 100K radian per second. And this also shows the phase plot. The phase plot actually, because we have 2 poles, right? So therefore the transition goes from the 180 degrees. In this case, at lower frequency, because we have 0 at origin. So in that case, at low frequency, we have 90 degrees. And at a high frequency, we have negative 90. So the total, the transition would be will be 2 times 90 degrees. Okay. So that's about the this lecture. I hope you enjoyed it. No matter what you do, remember that just never stop, right? Just keep going. It's very important. See you next time. Bye bye.